Okay, so I think we can start. Good morning, everyone, and welcome. It's a pleasure to open this webinar organized by the Water Europe Expert Group on water and agri-food. And I'd like to thank the expert group leaders and the speakers for bringing together, I think, what is a very relevant discussion and exchange. Water monitoring is, of course, increasingly becoming important as a strategic enabler for the agri-food sector. It supports both economic performance and environmental sustainability, especially in a context of growing water scarcity, increasing quality requirements, and pressure to optimize resource use. Better monitoring means also better decision making. And of course, across Europe and beyond, the agri-food sector is under increased pressure from climate change, water stress, and stricter sustainability expectations. Now, at the same time, technologies are, of course, evolving rapidly. We have a real-time monitoring, digitalization, microbiological control, predictive tools, smart data systems, AI, and decision support systems, along with new technologies that are changing how water can be managed in agriculture and food production. Now, at Water Europe, and I think that's not a surprise, of course, we promote a water smart society and economy. And I think in that context, monitoring is of critical importance of that vision, because you cannot optimize, secure, or circularize water systems without understanding in real time what is actually happening with them. This applies equally to nutrient management, water reuse, microbiological safety, and biofilm control. Now, today's webinar brings together concrete examples from research and industry. The focus will not only be on technology itself, but also on how monitoring solutions can support smarter, safer, and more sustainable agri-food systems, and importantly, how they can help move from reactive management towards operational control and predictive decision making. I encourage everyone to actively engage in the discussion and exchange experiences and perspectives. And with that, I would like to hand over the moderation to now Francesca, who will guide us to the rest of the webinar. Francesca, please take the floor.
Thank you, Dirk. Good morning, everyone. So thank you for joining today's webinar on water monitoring options to support the agri-food sector. This has been organized by the Water Europe's expert group on water and agri-food. I am a member of this group, and the leading is Charlotte Berger from Vito. I am Francesca Odino. I'm a principal researcher at Leta Technological Center. And our group aims actually to address water challenges faced by the agri-food sector to promote sustainability water management practices in agriculture and fruit processing, and facilitate collaboration between water and agri-food stakeholders with main aim of increased water resilience, promote the use of alternative water sources such as reclaimed water, reduce water consumption through water efficient practices, precision farming and digital technologies, and enhance sustainability, resilience, and productivity in the agri-food sector through innovative solutions and best practices. So this is the agenda. We will cover the following topics: nutrient monitoring in water and soil as a tool for fertigation scheduling, digital smart solutions for microbiological water quality monitoring, and the key role of biofilm monitoring in the agri-food applications. And we are very pleased to have 4 distinguished experts joining us today to share their knowledge and experience on sustainable water management, water quality, and innovative solutions for the agri-food sector. We have Anna Tallur from IRTA, who will present nutrient monitoring in water and soil as a tool for fertigation scheduling, a real-world application in the Apulia region in Italy. Montserrat Bayel-Ribas from Adasa, presenting Aqua Bio digital solutions for microbiological water quality monitoring. Luigino Grasso from Binovate Technologies is presenting smart water, turning microbiological risk into operational control. And finally, Giovanni Pavanello from Alvim, showing the importance of biofilm monitoring in agri-food applications. And then, of course, we will have some closing session with some key remarks. Remember that each presentation will last 15 minutes and it will be followed by a Q&A session. So you can submit your questions at any time in the chat. And I will then pose these questions to the speakers at the end of their presentation or during the Q&A session. So I guess that's all from my side. I can introduce the first speaker. So Anas Talou is a postdoctoral researcher at IRTA. His work focuses on sustainable water, soil and crop management, particularly in areas facing water scarcity and the impacts of climate change. His research explores the use of reclaimed and alternative water sources for irrigation, assessing both their agronomic benefits and their effects on soil health and crop quality. He also works at an interface between science and policy, contributing to the development of safe and compliant water reuse strategies while applying precision agriculture tools and circular approaches to improve long-term water resilience in agriculture. So, Anas, the floor is yours. Thank you very much.
Thank you so much, Francesca. Good morning, everyone. First, I would like to thank the Water Europe for organizing this important event and also to give us the opportunity to share, to exchange, and also to discuss about this thematic. So I will share my screen and present our result. Can you please confirm that you can see the presentation in the full mode?
Yes, now yes, we can
Now
see
it's
it.
okay. Okay, so I will present the nutrient monitoring in water and soil as a tool for fertigation scheduling, a real-world application in Apulia, in Italy. Mainly, it was a work that we developed a decision support system in order to manage and also to increase the water and fertilizer use efficiency in a scarce region in the south of Italy. So I will present briefly our institution, which is an Institute of Agri-Food Research and Technology. We focus on different areas and programs. We have plant production, animal production, food industries, and in each area we have different programs like efficient use of water, fruit growing, genomics, sustainable extensive crops, aquaculture, animal welfare, marine and continental waters, and also different programs. For me, I mainly work in the efficient use of water in agriculture program. In this program, the main objective is try to convert water resources into yield while minimizing the environmental footprint across three management scales at the level of farm, water districts, and also the regional levels. The research line that we work on in our program, we work on physiology and soil-plant water interaction, irrigation agronomy, fertigation, nutrient recycling and circular economy, remote sensing and crop water relations, digital tools for agricultural water management, governance of agricultural water, and the last one, which I'm responsible of, is the irrigation with alternative water resources, mainly reclaimed water and other sources like desalinated or brackish water. So I will first introduce the global water crisis that we are facing. Then I will talk about alternative water sources, and then a real application using this ReUpsal platform, which is a decision support system for nutrients and water use efficiency. And at the end, we can have some questions and we can discuss. So, as you all know, that we are facing a severe climate change, fostered also with high population growth, with a lot of generation of waste, deforestation, intensive agriculture, also the different industrial wastes, and also the overuse of different natural resources. And this lead to different results, increasing the temperature, the sea level rise, water scarcity, soil degradation and deterioration, severe weather patterns, and also like the spread of different pathogen disease. As we know that we are the amount of water that we have is really little amount, mainly groundwater, lakes, river, and also glaciers. But the 97% is mainly oceans, which is salt water, which is difficult to be used and applied directly in agriculture. And we know that agriculture consume 70% of water. So it's one of the biggest sector that consume water. Also, knowing that the water scarcity is affecting a lot of countries, mainly the Mediterranean countries. We are facing severe water scarcity, especially in the last decades. And we know that water scarcity is affecting at least 11% of the European population, is also affecting 17% of the European territory, and is affecting 20% of the population in Mediterranean, which they are living under constant water stress. And by 2030, the water stress and scarcity will affect the whole countries if we still go in this climate change pattern and water scarcity scenario. But at the same time, we know also that in Europe, we are producing like more than 40,000 million cubic meter of wastewater every year, but only 964 million cubic meter is reused. So we can know, or we can understand, that we have a huge amount of this reclaimed water that is not used, and we can use it as a potential in irrigation. Also, in the European context, we have like different countries that also they are start to have less precipitation. For example, in Spain, Greece, and South Italy, and they are facing some water scarcity. But at the same time, Spain and Italy, they are producing a high amount of reclaimed water. So at this point, they are using also some of reusing this reclaimed water in agriculture, but we cannot fully use this reclaimed water because of different constraints. So, as I said, that we have a great potential of reclaimed water, but in general, the alternative water sources are mainly reclaimed water, desalination and brackish water, atmospheric water harvesting, and rain water harvesting. Reclaimed water, we can say that we daily generate reclaimed water, but for desalination and brackish water, the problematic is they are not cost effective. So it's not easy to apply them in all the countries. While for atmospheric water harvesting, this water cannot be directly used in agriculture because this water is of high quality. So mainly it is used for drinking, is potable water. And for rainwater harvesting, you need a system to be installed everywhere in order to be, and then a filtration system. Then we can use it for agriculture. But it depends also on the annual precipitation and the location, and so it's not easy and cannot generalize quickly. So as you know, that reclaimed water is the water that is the wastewater that has been undergone at least secondary treatment with some disinfection process also. And this reclaimed water still contain different nutrients that can be valorized and used in the agriculture as natural fertilizers. And there are a lot of different use of reclaimed water, mainly in landscape irrigation, in natural parks, or for agriculture also, if they fit exactly the legislations and the regional or national guidelines. They can be used also in industry or for toilet flushing or in construction or different other use according to the quality of this reclaimed water. And the main problematic of this reclaimed water is still the electrical conductivity or the salinity, which can probably affect the plants or crop or soil. So this is why monitoring of quality of this reclaimed water is mandatory in order to be reused safely in agriculture. So the platform that I will present is called Reupsal, which is a platform for nutrients and water use efficiency in collaboration with IRTA and also the University of Aldo Moro of Bari in south of Italy. We work also mainly with Professor Alessandro Vivaldi, and we work on two different fields. One field of pomegranate and the other one of olive orchard. As you can see here, that in the south of Italy, in a district called Gallipoli, which was near a wastewater treatment plant that produced a tertiary treated reclaimed water. So the main idea of this study was to test two different plants. The first one is the crops will be irrigated with the reclaimed water plus conventional fertigation plan. This is the control, so we will not do any smart fertigation. We will use what the crop needs according to the crop needs. But the other plan is the plants will be irrigated with the reclaimed water plus smart fertigation. The smart fertigation is trying also to count the nutrients available in the reclaimed water so that we can preserve or we can save a good amount of fertilizers, and also we will increase the water use efficiency. So the Reupsal platform is connected to the sensors that are installed in the field. These sensors can give us ideas for about the parameters, soil parameters, about also reclaimed water quality. We have sensors installed in the outlet of the reclaimed of the wastewater treatment plant, and we have also sensors installed in the field. Also, we have irrigation logic controller that can manage the fertigation plan according to the need, according to the crop that we want to plant. So the architecture of this Reupsal is based on sensors and hardware for water and soil monitoring installed in the field. Is based also in the irrigation plan and the continuous monitoring of these parameters, and also it is based on the inputs that the user can add by himself, like regarding the crop variety, the season, the phenological stage, the fertilizer or the chemical fertilizer that are used. So you have a large set of information or data that you can introduce in order to have an exact fertigation plan. In this Reupsal can give you also the monitoring of the cubic meter applied and distributed over the orchard, and you can have it like monthly, weekly, and also annually. Also, the sensors and hardware for water and soil monitoring, we can see that we installed these two sensors that can give us like different parameters: ammonium, nitrate, potassium, electrical conductivity, pH level, temperature, and phosphorus. And what is good about these sensors is that they can continuously monitor these parameters, so you can know exactly how much nutrients you have, or if there is a problematic or no, according to this monitoring system. Then we installed also some sensors in the two orchard. We installed the Teros 12 probe that can give or measure the volumetric water content in the soil, the temperature, and also the electrical conductivity. And we installed 12 probes, 6 for olives and also 6 in pomegranates. They were installed randomly at two different depths. The first is 30 centimeter and also 60 to 70 centimeter. So the irrigation plan is based on soil moisture, mainly on soil moisture. So we program this irrigation plan when the soil moisture reaches the field capacity of 32%, the irrigation stop. And when the soil moisture drops under reaching the point, which is the 27, the system open the hydrants and the irrigation will start. Why we choose this range of moisture, because we know from the bibliography and the references that this is the good range that the crops like olives and pomegranates, they can spread their roots and they can have a good production. So this is the interface of this decision support system, Ryubsal. As you can see that you can have different parameters from water quality on the left, and then you can have the valves, if they are working or no. If there is a problem, you can see it here. And you have also the different parameters from the sensors in olive and also the pomegranate orchard. We have the selection of irrigation criteria that can be managed manually or also automatically. As you can see that the time of management, it can be organized or programmed weekly. This is the hour. What are the hours that you want to irrigate? If you want that is manual or automatic. This is the range or the set that you want when to open or where to close irrigation. And this platform also gives you the fertilization plan and also the contribution from the wastewater, from the reclaimed water, not wastewater. And also it can gives you the suggestion of fertilization plan. As you can see here, that we have 70 kilogram per hectare of nitrogen, and also for phosphorus and potassium. And then you can see the plan, how much you can save from fertilizers. Also, you can have the soil parameters monitoring continuously. You can check if there is a problem, if everything works well. And then you can ensure also that this plan have positive effect or no. And this is what we did in the field. So as you can see here, that we have different parameters that help us in precisely manage the fertigation plan. Yeah. So as you can see also here, that water quality monitoring, we can have the trend of different parameters, temperature, electrical conductivity, and also the pH. And then you can know and understand the variability and the fluctuation, if there are problems, when the months that we have high parameters, or we have a problem in water quality, or we have problem in temperature or electrical conductivity. Here we have the probes, or the soil moisture monitoring through the 6 probes that we installed. And as you can see, that we have 6 sensors that can give us the percentage of humidity, and then we can program our fertigation scheduling. You can also have the trend of nitrates. You can choose the date or the year, the concentration of the parameter that you want to monitor. And you can see, for example, here that we have the trend of total ammonium, the nitrate, and also the ammonium. Here we can have also the soil quality monitoring for the period that you want. You can have also the water content from the different depth, and also the electrical conductivity. For the fertigation scheduling, you can see that in this platform, we have also the available nutrients in the soil, and also it counts the needed fertilizers that we need for both crops, for olives and pomegranates. You can see, for example, for olives, we have available nitrogen, so we can count it in our smart fertigation plan, and then we can save if you count it for 1 year or 2 years of application, so you can save a lot of fertilizers and also a lot of money. For the smart fertilization plan in case of olives, as I said, that for the control we didn't count the reclaimed water contribution. So we apply directly what the chemical fertilizers that that the crop will need without counting or without taking into consideration the reclaimed water. But for reusal, we counted the contribution from reclaimed water, and as you can see, that we saved 30% of nitrogen, 5% of phosphorus, and 56% of potassium. And for pomegranate, we also saved 11% of nitrogen, 1% of phosphorus, and 29% of potassium. So and also we the yield when we for the harvesting, we didn't find any significant differences between the reusal crops and also the control, which means that this platform help us in reducing the fertilizers inputs and also saving water and saving money. And at the same time, we preserved the same yield, and as you can see. We did also some physiological parameters like the chlorophyll content index for olives and pomegranate, and we didn't notice any significant difference, and the trend were normal in all the phenological stage for olive and also for pomegranate. Also, we did some fruit qualities, and we found that there is no effect of using this reclaimed water in the short term, but further studies also should be done, like to know what is this impact for the long term on soil salinity and also on crop quality. So, as conclusion and recommendation, we can conclude that it's mandatory for us now to use these digital tools because they help us in reducing the chemical inputs, they help us in saving water, and also to preserve the environment and to give to the plant the right amount at the right time. So this is the benefits from these digital support systems. And the recommendation that we need also to do further investigation for the long-term impact of this reclaimed water. Also about the scalability, we are still like working on different activities of this platform to try to scale it in other regions from the Mediterranean. And also, we need to validate different sensors and different sensor quality because also about that the sensors help and give accurate measurements and also help us also in monitoring different parameters. So more parameters we have, more precision we can do. And nutrient uptake and efficiency analysis, we can also understand variation in nutrient uptake across different crops and can promote better fertigation strategies. Thank you so much. And if there is any questions or comments.
Okay, thank you, Anas. Thank you very much. So we have a question from the audience. Do you have an idea about the return on investing sensors and platform versus savings on water and fertilizers?
Yes, this is something a good question, and that we are still working on because it's not easy because the farms are very large, and we are still working on counting the benefits and the cost of this having this reclaimed water. But the problem is that it's a necessity, not just something that we want to do or just to try, but now it's the necessity, and it's mandatory to switch to using different alternative water sources like reclaimed water, because in the south of Italy it's agricultural zone that produce mainly 40% of the Italian agricultural products, and also it's facing a lot of problems, water scarcity first, but also other spread of other disease like the Xylella fastidiosa. So this something that we should also study in the future.
Okay, thank you, Anas. And there is also another question. How many sensors per hectare were placed in the olive fields in Puglia, and how expensive they were? Did you consider integrating spatial information? And
yes, for example, the orchard of olive is 1 hectare, and in 1 hectare we installed 6 sensors. So and it was 6 sensors were installed randomly, and for the pomegranate we installed 6 sensors. These sensors vary also about for the price, but in general, if you want accurate data, the sensors is about like 8,000 euro, more or less. But there are other sensors that are cheap, but the problem of the accuracy, they don't give you like accurate results, and also they are not robust. They can have some deficiencies. So this is the main problematic. But in general, if you count also that reclaimed water is also paid, so if you use these sensors and you count them in 1 year or 2 years, you are going also to save a lot of money, because reclaimed water is like 0.40 cents or euros per cubic meter. So this is also something you should take into consideration.
thank you, Anna. I also have a question, a last question, I guess. And I would, because we have seen that these applications can be very important for saving both nutrients and water. So this can have an impact, an economic impact on also from the farming point of view, so for the farmers themselves. So I would like to ask you how far we are, from the real large-scale application of these digital tools for decision making at farm level, and which are, in your opinion, the main barriers that the farmers have to face? It's just the main one, I guess, it's the cost, as you explained, and I don't know if there are some others, and how can we or policymakers speed up the process? In your opinion, how we as scientific community or policymakers can speed up this process of digitalization?
Yeah, thank you, Francesca, for this question. We all know that there is a gap between the research and the real farm applications, and this is mainly because everyone is working on its own. Scientists, they are trying to work on its own, but there is no synergy between the different stakeholders. And Europe now is trying to fill this gap by promoting different projects where all the stakeholders should be or must be involved, involving the irrigation communities, involving agricultural cooperatives, and also involving research center, universities, and creating some living labs also that can foster and that can help in filling these gaps. The other problematic is also the awareness of farmers about these digital tools. There is also a gap that need to be filled by continuous creating this event, for example, and trying to do some seminars, trying to help farmers to provide some services that they can help them in using these digital tools, because digital tools, they serve also when you have large fields, because when you have a large field, you cannot check every plant, but you can use digital tools to check from the satellite, or using drones, or using airborne, to check the problematics, the irrigated and non-irrigated lands, to check the problematics, the disease, if there is water scarcity, salinity. All these parameters can help us a lot in promoting sustainable agriculture.
Okay, so thank you, Anas. Thank you very much for this nice talk.
Thank you.
And so we have seen that how critical it is to monitor nutrients and water in real time. However, when we move from agronomic performance to microbiological safety, new challenges arise, and our next speakers will present innovative solutions and approaches to help address these challenges. So we move to the next speaker, which is Montserrat Valle, who will present AquaBio digital solutions for microbiological water quality monitoring. Montserrat is Senior Innovation Specialist at Adasa Sistemas, a global leader in water, environmental and weather technologies. She holds a degree in biology from the University of Barcelona and a master's degree in water technologies from the Polytechnic University of Catalonia. With more than 35 years of experience in the water sector, she specializes in water quality monitoring, analytical method development, and online sensing technologies. And for over 25 years, she has led the analytical area within the Adasa's R&D department, driving the development of innovative monitoring solutions and measuring devices, several of which have resulted in patents. So, Montserrat, the floor is yours. Thank you.
Thank you very much, Francesca. And thanks to Water Europe for the invitation today. Today I will talk about digital solutions for microbiological water quality monitoring that can support the agri-food sector to ensure safety, mainly, and to improve efficiency and operational continuity. And let me first do a short introduction about Adasa. At Adasa, we design digital solutions for public and private organizations worldwide to address integrated water source management, urban water systems, and water-related climate challenges. We have more than 40 years of experience innovating in water cycle, and we are more than 200 professionals with headquarters in Barcelona, and we have offices in Spain, the Netherlands, and Australia. And since 2020, we belong to the German group Ski on Water. We are highly specialized in urban water digitalization, catchment management, and hydrometeorology, and as well, as is today the matter, the development of online measuring device for water quality measurement. During the period from 2020 to 2024 in Catalonia, we experienced a long period of droughts that led to a shortage of water resources. The reservoirs, as you can see here in the picture, were in a very critical situation. We had 3 extreme drought episodes that these episodes prompted the government to declare the state of emergency. And this meant that the episodes introduces a series of restrictions that affected agriculture, with cuts that were ranging from 25% to a complete suspension, and for the water use in agriculture, and for industry it was between 5% and 25% during the emergency status. And in this context of climate emergency, the government of Catalonia has prioritized the water reuse in its policies and investments for the next 5 years. And we see that for this reason, the water regeneration is increasingly becoming an essential source of supply for both agricultural, irrigation, and industry. But the sanitary quality of the reclaimed water must be warranted, as is stated in the Royal Decree 1085 in Spain, and by the European regulations as well, that establishes that the reuse criteria in which ecology is the main microbiological quality indicator, and it says that it must be monitored and at a defined frequency for the use of this reclaimed water. And to help our clients to manage the risk of microbiological contamination in the water reuse in their operations, and as well to comply with the regulations, we developed these two solutions, that is Aquabio, that it's an automatic and continuous online measuring device for the quantification of E. coli, and B. coli, that it's a real-time prediction E. coli based on artificial intelligence. Let's start by Aquabio. And let's say that unlike the laboratory methods can take up to 96 hours to obtain a result, and you have to sample, to transport the sample, to analyze the sample in the laboratory, and then counting and reporting. The Aquabio, it's an automatic and continuous measuring device that avoids all the practical restrictions, such as the time of the day, if it's weekend or not, the laboratory availability, the weather conditions, if there's personnel available for sampling. As it provides us with the immediacy in taking the sample, because it's located on place, and only takes from 5 to 12 hours to give a result, depending on the concentration. And in addition, Aquabio has the ETB verification, which is an independent verification promoted by the European Commission that currently is an ISO, that it's ISO 14034, and which guarantees that the data provided by Aquabio is reliable and the users can make decisions derived from monitoring with Aquabio with complete confidence. Another important issue is that while laboratory methods provide occasional measures, Aquabio provides continuous digital data, allowing digitalization process and, in consequence, optimization of the processes. Here you have some features of the Aquabio. These ones ETB verified, that as is the range, that goes from 1 to 10 to 5 E. coli per 10 milliliters. The detection limit, we can detect 1 E. coli in 100 milliliters. And the quantification time, it's from 5 to 12 hours, depending on the initial concentration. As well, we have a short maintenance of 50 minutes every 15 days. And from these 50 minutes, 30 are each waiting time for the disinfection process. Here you have other features about the integration in the communication systems. And how does it work? Aquabio, it's based on the defined substrate technology. That means that when you introduce the sample in the sample is automatically introduced in the system, and we mix with a reagent, and this reagent contains a substrate that is specific for E. coli, and this substrate has a particle linked to the substrate that is colorless. But when the substrate is degraded specifically by E. coli, this particle is free in the media and is fluorescent. This means that as E. coli is growing, the fluorescence is appearing in the media, and we start monitoring. Monitoring with optical system every 2 minutes until the moment in which the system can detect the fluorescence, and it's in this moment is correlated with the initial concentration of the E. coli in the way and inversely proportional. This means that as much time takes to give a result, less initial concentration, and less time, higher initial concentration. And here we can see some examples where we have installed the device. For example, in wastewater treatment plants, in some cases at the outlet of the tertiary treatment for irrigation purposes. or at the outlet of secondary treatment to improve the efficiency of the tertiary treatment. Here we have some examples all over the world. We have as well in the industry, in the beer industry, to monitor the wells, for example, in this case. And regarding bathing water, we have stations in Somorrostro and Bogatell beaches in Barcelona, in Mallorca, or in Montevideo, where we have forestation. Aquabaio can work in surface water, as for example, in an installation we have inside the boat in the Spree River in Berlin, or in Bangkok Bay in Thailand, where we have for the coastal water measurement, we have 6 stations. And as well for groundwater where we have in Israel several stations. And our latest deployments are in L'Ampolla drinking water treatment plant as an alert system in the pumping station, and in this case at the outlet of the tertiary treatment in el Prat de Llobregat wastewater treatment plant. That is one of the 2 wastewater treatment plants big facilities in Barcelona, and in 220 they provided 54 million cubic meters of reclaimed water for different purposes, indirect potable reuse industry and for irrigation. And is in the line of irrigation when we installed the Aquabaio, as you can see in the picture. And another installation is in the community of irrigators of Riudecanyes. In this case, the installation is in the reception point from the water coming from the wastewater treatment plant of Reus. They suffered a lot with the drought, so they started the process to bring the water from the outlet of the tertiary treatment in the wastewater treatment plant. And so they decided inside this digitalization process, they install an Aquabaio. And in the case of the food industry, and following the Spanish regulation, it is required a special permit from the health authorities. And this is the case of the slaughterhouses. We developed ecology to provide a predictive layer to Aquabaio and to give confidence to health authorities in the use of reclaimed water. Ecology provides Aquabaio with a real-time predictive capability. And how does it work? Ecology, it's a virtual sensor that it's based in artificial intelligence model, a prediction system and a control sensor. And in a first phase of training, we introduce all the data, process data, laboratory data, historical data, continuous measurement of physicochemical parameters and weather data, and as well with results obtained with Aquabaio, and we obtain estimated value of ecology. But in the second phase, that is the execution phase, the prediction system works just with the continuous measurements of physicochemical parameters to provide an estimated value of ecology. That is compared with the value provided by Aquabaio, and this result is introduced in the system for retraining. And it consists in these 2 devices, the installation, that is an Aquabaio that measures Escherichia coli and total coliforms, and an Aquatest MO, that it's a multi-parameter device developed for us as well, that measures pH, conductivity, redox, temperature, dissolved oxygen, absorbance at 254, absorbance at 365, and turbidity. All the information provided by these 2 devices is stored in the cloud, and through Ecodata, that it's our platform for data visualization, we acquire and visualize the data provided by Ecology. We installed the device in the outlet of tertiary treatment in the slaughterhouse of Avignon. And currently they are using the reclaimed water for forest irrigation and to irrigate some crops. But in short, they when they improve the tertiary treatment, they want to use the water for the cleaning of the trucks and livestock pens, that which would account for up to 50% of the total water consumption. That currently it's drinking water. They are consuming drinking water, and to do this, as is it is the food industry, as we have said, they require a special permit from the health authorities, and ecology helps them to build confidence for the approval of this use by the health authorities. And here you can see some results obtained with the virtual sensor. You can see here in blue the AquaBio and in green the ecology. And we use it for the calculation, the XGBoost model, mathematical model, that is a network, neural network model. And here you can see the different weight of each of the parameters in the model. You can see that the redox has a lot of weight, then the compensation, that it's absorbance 365, precipitation, temperature, turbidity, and so on, from more to less weight. And the accuracy of the prediction is around 92.25%, and the error measured between measurements and predictions is 5.33. That is very good. And just to conclude, some conclusions about the technology. And I would like to say that the real barrier for water reuse is not the technology, it's trust. And the technology is there and it's reliable. And AquaBio helps to digitalize, improving responsiveness, decision-making in water quality management. And regarding risk, safe water reuse depends on effective microbiological risk control. And as final conclusion, let's say that AquaBio, it's a valuable digital tool for building trust and managing risk in reclaimed water reuse, while ecology provides this predictive capability. And thank you very much.
Thank you, Montserrat, for this nice presentation. I see that one participant has raised his hand. I don't know if you have Roman Cibolka. I don't know if you have some questions for Montserrat. I don't see. I have a question. Okay, we have, but in the chat we have a question. Is hormones checked in this method?
No, it is just checked in a very specific way. Ecology, that ecology is the parameter that all the regulations used to use as a control microbiological risk parameter.
Okay, and then there is another question. What's the need for the ecology predictive capability using ecology when I can measure it with the AquaBio?
For the ecology, you need systems. You need measure some real online measuring devices that like pH, conductivity, and we train the system with AquaBio. I don't know if I am replying the question.
I think that he's asking why you have to use ecology if you already have AquaBio. I think that ecology is more for predictive, decision-making process, to assist the decision-making.
Yeah, because AquaBio provides a result in 5 hours or 12 hours. The strength of Aquabio is that it's a verified method by ETB compared to the laboratory. And Becoli, it's a virtual sensor that provides continuous values. Let's say it's like if it was a pH or if it was conductivity. But the strength of the system is that you are training the virtual sensor with continuous real data from the Aquabio. Okay.
Yes, thank
The
you.
difference is time, let's say.
And there is another question from the audience. It seems the devices are field-based ones. Are there portable ones?
No, at the moment. You need some kind of installation, as you have seen in the pictures I showed. There's no portable one at the moment.
Okay, thank you, Montserrat. I have just one question also in this case, because it's clear that this online real-time monitoring can help the decision-making process in the agricultural or agri-food sector through use. So, and it can assist and let's say the safety of reusing reclaimed water. So since the advantages are clear, I would like also in this case to know, in your opinion, so which are the barriers that we have to address and face to spread these the use of these monitor tools in the agri-food sector, and also is from a regulatory perspective. Do you think that in the future they will include this online monitoring as a standard requirement?
Yes, I think that for online monitoring in general, the real barrier is the regulation, because it may seem opposite, no, one to the other, but in fact, the regulation says that you have to measure once per month, once per week, and you have to measure in a laboratory. So this is a real barrier for online monitoring and for the improvement of the systems. I think in short, this will be fixed in the regulations, because it's very important to introduce digitalization in the control of any process. No? And this is what allows to introduce the digitalization, to have online monitoring device, because in fact it's IoT systems. No?
Yes. So thank you, Montserrat. I guess we can move to the next speaker. So let's see that, it's clear that we have to move just from water quality measurement to anticipating the risks and translating it into actionable control strategies. So the next speaker, Luigino Grasso, will address these challenges, presenting smart water, turning microbiological risk into operational control. Luigino Grasso is Chief Technology Officer at Binovate Technologies, a company specialized in rapid and automated microbiological monitoring for water applications. He holds a master's degree in chemistry and a PhD in biophysics from the Swiss Federal Institute of Technologies in Lausanne. He leads Binovate's R&D department, where his team develops automated instruments, digital solutions, and innovative analytical methods designed to make microbiological water quality monitoring faster, more accessible, and actionable. His work focuses on product development, technology strategy, and transforming scientific innovation into reliable industrial solutions that help address real-world water quality challenges. So thank you, Luigino, the floor is yours.
Yeah, thank you, Francesca, for the kind introduction, and also thank you for the opportunity. I must say that I'm also very pleased to present after Montserrat, because I'm going to also talk about automated microbiology. And when I started working in this field almost 10 years ago, most of the discussion we had around this topic were with scientists, R&D teams, or innovation departments. And basically at that time, online microbiology was often seen as something quite niche, mainly linked to lab research work. So today, the fact that we have these two presentations on that topic in a webinar with such a large audience show that something has changed, and I think it's a very positive evolution. Because microbiology is no longer seen as a lab topic, but more becoming an operational topic. So just try to share my presentation. So basically today I will not only speak about sensor, but really about the shift we see happening in the water industry and also in the agri-food industry, the shift from microbiology as a compliance test to the microbiology as a practical tool for operational control. So, but before we go into the topic, just a few words about Binovate. So Binovate is a Swiss company based in Lausanne. We develop and manufacture water quality analyzer for online microbiological monitoring. We are active in different sectors, utilities, food and bev, manufacturing industry, and with application that goes from drinking water to ultra pure water, such as in the pharma or the cosmetic industry. Our objective is not only to provide measurement device, but really to help water professionals to integrate microbiological information into their daily decision-making process. And with that ourselves, but also with the help of a global network of distribution and service partner around the globe. So we already saw that with Montserrat. Traditionally, microbiological water quality has been managed through this following sequence: sampling, lab, weight, report. Basically, an operator needs to take a sample, send it to a lab, and then wait several days, depending on the method or the parameter that is measured. And finally, a result is received and documented. Of course, this approach is essential. I want to be very clear about that. Lab tests remain critical for compliance and regulatory purposes, but from an operational perspective, it has clear limitation. First of all, the result comes after the fact. By the time the result is available, the water may already have been used. Secondly, there's no visibility between samples. We know something at the moment when the sample is taken, but we don't know what happened before or after. And the third limitation is that this delayed information has a really limited value for a real-time operation. We have seen that the agri-food sector is facing a number of water-related challenges that were discussed in the previous presentation. But what is important to note is that they all have a microbiological risk associated. So the role of microbiological monitoring needs to evolve to be able to manage this risk. For example, we talk a lot about water scarcity, so many industrial sites under pressure, so they need to reduce freshwater consumption and then consider reuse with all the microbiological risks that are associated. Climate variability, source water quality are also becoming more variable because of extreme weather events, for example, that can then influence the microbial quality. Safety, of course. So in the agri-food sector, water is basically everywhere. It can be an ingredient, it can be used for washing, rinsing, cleaning, cooling. So if there is a microbial drift, this can become a product quality issue and then finally a business continuity issue. And finally, efficiency. So producer want and have to use less water, fewer chemicals, less energy, and avoid the unnecessary shutdowns. So to be able to optimize also in a safe way, they need data because without data, the safest approach is often to overtreat, overclean. So basically, this is the link with microbiology. The more we want to reuse, reduce, or optimize, the more we need microbiological visibility. So this basically brings us to the concept of an operating loop, basically. On the left, again, the traditional approach, and on the right, what agri-food operation needs. Rapid monitoring, trend analysis, and then action, and it goes like that. So when this data becomes available, more frequently operators, they can start to see trends. So they can then distinguish between normal variability and abnormal events. They can then detect a drift before it becomes a problem. And then they can also define action based on the situation, because that is what I mean by turning microbial risk into operational control. The measurement itself is important, of course, but the real value comes when the measurements support, in fact, decisions. And this is where the BacterSense comes in. So BacterSense is our flagship product at Binovate. It's our rapid microbiology analyzer that was designed for water application and, of course, industrial operators. So it can detect all the bacteria present in water in only 20 minutes. It's a fully automated and connected instrument, which means that it can support continuous monitoring of water network, treatment system, and any type of industrial processes where there's water, basically. And importantly, it's redesigned for industrial environments. So they need reagents, but they are all contained in a hermetically sealed cartridge. And once this cartridge is inserted, the device can operate fully autonomously for up to 1,000 measurements, which means, depending on the frequency, that there's no human intervention for several months. And of course, the device can be operated in every industrial settings. Like it has to be seen like a sensor, like it would be a pH or a turbidity or a conductivity sensor. Just a few words about how it works, basically. 3 main steps. First, the sample preparation. So the instrument takes samples, either from a water system, a water pipe, or also from a sample tube, if we want to do like manual measurement. And then the bacteria are stained with the reagents that are in fact contained in the cartridge. The staining makes it possible to clearly then distinguish between viable bacteria and dead bacteria and particles. Then the sample passes through an optical system where a laser basically excites the stained bacteria, and the fluorescent signal is measured and the bacteria quantified. So finally, then the results are delivered, and the instrument generates quantitative bacteria count, but also time series. And this is what is important for operators, is that the result is not just a number on a screen, but it becomes part of a trend. And once it becomes a trend, it can be used to understand the process. So what we think is that is where the rapid microbiology becomes much more powerful than isolated testing. We talk also a lot about digitalization, and we like to say that we are also digitalizing microbiology because this is a very important point. And when we talk about digitalization in the water sector, we often think about flow, pressure, and energy consumption, but microbiology has often remained outside this digital layer. And with BacterSense, so we can start to bring microbiology into the same environment as this other parameter. So BacterSense can provide information locally on the screen, but also it can be connected to a PLC, SCADA system, and also we have a cloud platform called Bacter Cloud that can also be very useful for fleet management or for more advanced data analysis. So this slide just illustrates the difference between offline, which is a traditional way, offline monitoring, and online monitoring. So in the offline approach, the operators, we already said it, the operator takes the sample and brings it to a lab. And then the result, basically it only gives a snapshot of the situation. While in the online approach, so not only the sampling and the analysis can happen directly at the sampling point, which is very important, but this also allows operators to follow these microbial changes over time. And this is very important because microbial water quality is very, very dynamic. It can be stable for a long time and then change suddenly because of a rainfall event, treatment failure, or any change in the operation. So this is the difference between asking, was my sample compliant, or asking, is my water system fully under control? And I think this is a very good, very important point. Yeah. So let me move now from the concept to some application. I will just briefly show 3 examples where BacterSense can support the agri-food industry, but not only, and because we are here talking about any water-related operation. So the first one will be about source water monitoring, second about water reuse, and the third one about pilot qualification. These three different applications, they in fact use the same logic, measuring at the right point, understanding the trend, and then use the data to support operational decisions. So the first example is spring water monitoring. And this is very important for many food and beverage producers. Source water, in fact, is one of the most critical resources. But source water, its quality can change very quickly, as I just mentioned it. Heavy rain, seasonal changes, catchment events can cause this rapid shift in microbial quality. So if these shifts are detected too late, contaminated water may then enter the production line. So the graph shown here illustrates a bit the fact that different wells can also behave very differently. One source may be stable, while another may show a significant deviation. So it's why with rapid monitoring and automated online monitoring directly at the catchment, the objective is to detect these changes before the water enter the process, so that then operators can then decide to divert the water, to treat it differently, or why not to investigate further to understand the issue. And another very important topic is that it also provides audit-ready data. So instead of relying only on isolated laboratory results, the operator can show then continuous evidence that everything is working fine. That can be very important for showing that to, I don't know, auditors, depending on the type of industry. The second example is a pioneering project of water reuse. We are here in Belgium, in Hofstede, and basically it's the first direct potable reuse project using municipal wastewater in Europe. The project has been initiated and developed by Water Uni. It's a joint venture between Faris and the Devater Group. So when we talk about direct potable reuse, the level of public scrutiny is obviously very, very, very high. And also there is a technical risk and some regulatory attention. So in such application, manual testing alone is not sufficient to demonstrate control in real time. So it's why Water Uni has placed a Bactosense at the very end of the treatment with the goal to automatically stop the plant in case of abnormal changes. So, but the benefit is clear, is a 24/7 confidence, a smarter risk control, and also, in fact, a reference approach that can then support future reuse initiative. And for the agri-food, I think there's also a lesson, because whether we talk about potable reuse or processed water reuse, the same question comes back: is how do we demonstrate that the system is under control? And so at Binovate, we think that the Bactosense, but any online monitoring system can in fact help provide that evidence. And finally, my last example, it's about pilot qualification. It's also a project we had in the water reuse space. So in fact, in many reuse projects, the pilot phase is very critical. So before moving to full scale, the user, the developer of the solution, they need to understand the treatment performance. And it's where a multi-point microbial monitoring become very important, because then we can follow the treatment train at different locations: feed water, the intermediate tank, all the different treatment steps, like reverse osmosis, the output water. And here, basically, we also have developed, Bactoswitch. Bactoswitch is basically an add-on to the Bactosense that can connect the system up to 4 different water streams. So basically, this makes possible to compare then microbial counts before and after a treatment, like filtration, for example, measure performance, as we see here on the graph, like log reductions, and also then detect changes in membrane behavior, for example, or any treatment efficiency. And I just want to finish my my presentation with just a practical 30-day that we call a path to operational control, because it's important to basically understand how an organization can start working with online microbiological monitoring with device like the BactoSense. We often hear that it might be complicated to install, to change the habits. But in fact, the path is not so complicated, and the approach can be structured in 4 steps. First, we need to map the risk and identify the water points where microbiological change can affect the safety or the quality or potentially downtime. So this could be, as we saw, source water, treatment steps, or the final water. Second, we need to build the baseline by running the BactoSense measurement at these critical points and learn what normal variability looks like. And this is crucial because it will define what is an abnormal change. Third, then we need to define the action. Because the objective is not only to generate warnings, the objective is really to translate this deviation into operating actions. For example, hold, divert, disinfect, resample, clean. So this is really one of the most critical parts. And finally, the 4th step, we connect the system and we scale. So once the data and action are understood, the system can be connected to the existing workflow and fully digitalized. So the message here is also simple, is turn data into action. And I will just conclude with my key message. So basically, rapid microbiological monitoring is not only about finding risk faster, but it's really about operating water system with confidence. It is about improving safety. It is about supporting scale, especially when we talk about reuse or any circular water initiatives. And it is also about bringing microbiology into the digital age. And thank you very much for your attention.
Thank you, Regino, for this very nice presentation. There is a question from the audience. What specific microbiology species can BactoSense detect, and what is the tested accuracy error percentage?
Yeah, so today I didn't go into the detail, but basically we have at the moment 3 different cartridges that can be connected to the system, and we choose one cartridge depending on the application. The first one is called TCC, total cell count. Basically, we count all the bacteria that are present in water. So there's no specific detection. It's all the bacteria, whether they are dead or living or whatever. This is very important for groundwater monitoring. So we want to see really the total amount of biological life in the water. Then we have ICC, is for intact. We have only the intact cells, so the viable cells. And this is important for when there is, I don't know, a treatment process like chlorination and so on. So we only detect the bacteria that survive this treatment. And finally, we have another that is called ACC for active cell count. There it's only the cells that are metabolically active, potentially the most dangerous one. So today we don't do specific detection, but yeah, stay tuned on our channels, because there's some info that will come later this year, basically.
And well, the next question, I guess you already answered, but what is the relevance of monitoring all bacteria? Is this sensor selective towards fecal pathogens? Water hygienic safety is not related to bacteria in general, but to the presence of pathogens. So they are.
I think it's clearly important to mention that there are different ways to answer that question. But first of all, is by measuring the total load of bacteria. So you make sure that you don't miss any microbiological issue. You know, when you measure E. coli, I know E. coli is the world standard. Is the world standard for any fecal contamination event, but in fact, it's we don't measure E. coli because of E. coli. We measure E. coli because potentially it's an indicator of a fecal contamination that then contains other pathogens. So the advantage of measuring with BactoSense is that, in fact, you have a full picture. But then I can take also the example we discussed about filtration. When you want to understand the treatment efficacy of your system, if you only measure E. coli, basically you will have 0 before and 0 after. So it's not a parameter that can be used to optimize a treatment process. While when you look at the global population of bacteria, you can really have a clear indication of the reduction in the number of bacteria. And these bacteria are often linked then to potential contamination.
Yes. Thank you, Ludina. Yes, I think that, well, this is like we are in this digital AI revolution area. So I guess that we are all going, we will take profit. I mean, that all the industrial and the agri-food sector should take profit of this. And I guess that the integration, as you said, it's not just about warnings, it's about taking actions. So I guess that we need to integrate not just E. coli monitoring tools. We need to have an effective integrations to then translate these warnings, several warnings, into actions and decision-making process in general. So how far we are, in your opinion, from this effective?
In fact, as I started my presentation, we were very, very far away some years ago. I think now we are taking the right direction. There are some industries that are moving faster than others. I can take an example of the pharmaceutical industry. I think they released a new GMP good manufacturing process document several years ago, where they specifically mention online monitoring and integration of this data into the system, not to replace standard microbiological tests, but really to improve the safety, to improve the operational management of their water systems. In the drinking water also, things are moving, but it's maybe more like country initiatives at the moment. Some countries are much more advanced than others. And I think same goes for the agri-food industry. It depends on the company, how they want to. Probably we would need some help. In fact, regulation, it's a term that often comes. So we need, in fact, some help from regulators and so on. We need help because we genuinely think that what we do, but like Adessa just presented, that what we do is the future, in fact. I mean, I'm sure that in 10 or 15 years, there will be an online microbiological sensor installed in every water systems. If it will be a BactoSense or another, I don't know, but it's sure that it will come. So now it's more how fast how fast it will be.
Okay, thank you very much. So we are a bit short on time, so we move forward to the last speaker, Giovanni Pavanello, who will give a presentation on the importance of biofilm monitoring in agri-food applications to finally analyze sources of contamination that are harder to manage, even with strong monitoring and control systems. So Giovanni Pavanello is director and co-founder of Alvim Company. He holds a master's degree in marine biology and a PhD in environmental microbiology. Before founding Alvim in 2012, together with colleagues from both public research institutions and private industry, he worked for several years as scientific researcher at the Italian National Research Council. His experience bridges scientific research and industrial innovation, particularly in the field of environmental microbiology and water-related applications. So thank you, Giovanni. The floor now is yours.
Thank you. Thank you for the introduction and for the great opportunity to present to this audience. So just to give you a brief background about our company and where we come from. We are a small company that is based on a long history of scientific research, because the phenomenon we exploit was firstly studied in 1976, so 50 years ago, at the Italian National Research Council. And some of the researchers involved in that kind of study that was later on carried out worldwide. And some private companies here in Italy established AVIM in 2012 here in Italy. And in these 14 years, over this period, the use of this technology has widely spread. So AVIM system is currently used in more than 40 countries in the 5 continents worldwide in many different applications, as we will see. So about the basics, most likely many of you are aware of biofilm related issues, but just to make a quick recap, you know that in most cases, people just look at those bacteria free in the liquid, but these have a very small percentage of the total contamination in any kind of process, not just water. And even few bacteria from the liquid can settle on surfaces, giving rise to the so-called biofilm layer that includes the vast majority of contamination in any process. So easy to see that just looking at water samples or liquid samples and analyzing them gives a limited understanding about the total contamination, the total presence of bacteria in a process. Moreover, this huge reservoir of bacteria, the biofilm, can spread through the whole system downstream. So it is never a localized phenomenon. It spreads like an infection in any kind of application using liquids, not just water, as I mentioned earlier. And AVIM technology is already used in all these industries, ranging from cooling towers, for example, for Legionella prevention, to food and beverage, to prevent outbreaks and contaminations. Drinking water, and it's to say, hospitals and ducts, pulp and paper, oil and gas, and many others. Because biofilm causes a number of different issues, ranging from corrosion, when biofilm grows on metal, equipment failure, filters, loss of heat exchange efficiency, for example, on heat exchangers. And one of the most important topics is the increased resistance to biocide and sanitation treatments. Because if you treat an early biofilm, it's quite easy to get rid of it because it's not much protected. So free-floating bacteria are first killed by chemical or physical treatments when you apply them to a process because they are not protected. But also the early biofilm can be easily removed. On the contrary, when you go to a mature biofilm, most treatments will eliminate only the external layer, while underlying bacteria will stay alive and will continue to proliferate, including pathogens. So it's easy to see that to prevent pathogens, it is of uttermost importance to prevent biofilm. And this is exactly where our technology places, because we tell to users when biofilm is starting to form, and this is the best time for treating. So our technology is based on a bioelectrochemical phenomenon, commonly known as ennoblement. Very in brief, we detect biofilm growth on the sensitive surface of our probe, and without any biofilm, we have a small flow of electrons, a small electric current from the surface of the probe to the oxygen free in the liquid. So with no biofilm, you will get a flat signal baseline from the sensor. When biofilm forms, due to its biological activity, this flow of electrons increases. So it is important to note that this kind of phenomenon, bioelectrochemical phenomenon, is directly mediated to the biological activity of bacteria. So we do not infer the presence of bacterial biofilm as other technologies based on ultrasound or on heat exchange do. We directly measure it. So with biofilm, you will get a fast increase in signal, and it's very easy to understand what is happening, because with flat signal, you know that everything is okay, that no biofilm is growing, while fast increase in signal tells you that you need to treat, or if treatment is already applied, it is not enough to get rid of biofilm completely. This kind of technology detects the first layer of bacteria, not the thickness, but as we have briefly mentioned, the first layer is the most important phase because it's the right time for treating. So once it has been detected signal will reach a plateau, will not increase anymore. This is an overview of a standard Darwin system. One or more sensors can be deployed depending on customer choice. One sensor can be enough for small systems, one single production line, or where the conditions are similar through the whole process, while more sensors can help to monitor different conditions inside the system or different production lines. And data from the sensors can be directly acquired from industrial controllers, PLC, DCS, SCADA systems, and so on. Small installations or pilots can even acquire data directly from a computer or from a data logger. So what are the advantages of online real-time biofilm monitoring? The first one is the focus on bacterial biofilm, not on general deposit, because if you need to check and optimize a biocide treatment, you cannot rely on monitoring of deposit of general fouling. You need to focus on bacterial biofilm, as this technology, AVIM technology, does. And this provides very high sensitivity. So in this way, it is possible to detect biofilm growth long before it impacts the process, long before it represents a risk, and even before most lab techniques. And importantly, monitoring is possible in real time. No need to wait 1, 2, 3 days to get results from lab. And here there are some real-life application cases. This one from reverse osmosis desalination, where the data you see in the graph were from the sensor installed in the feed of the system. And before applying AVIM technology, customer here does chlorine continuously, 24/7. Then sodium hypochlorite was dosed only when biofilm was developing. So you can see that initially flat signal marked no biofilm, then fast increase in signal indicated biofilm growth, and so customer dosed sodium hypochlorite. And you can note that in this way, signal dropped to the original level, marking that biofilm was fully removed. When it grew again, a second dosage was applied, and again biofilm was fully removed. With this new wiser approach, compared to the previous original approach that was continuous dosage, it was possible to cut by more than 90% the use of chlorine, so huge economic saving and also huge reduction in environmental impact. And most importantly, there was no loss in process efficiency that is very important for membranes. And the question is, what happens when a treatment is not fully effective? This is a data set by Total Energies, the French oil and gas and also alternative energies company, who adopted this technology several years ago. So you can see that initially flat signal marked no biofilm, then biofilm grew, and so they treated. You can see that after this first treatment, signal dropped to the original level, so good, biofilm was fully removed. Then it grew again. So a second treatment was applied, but you can note that after this second treatment, signal was higher than before, and also the incubation time was much shorter. So the treatment was not fully able to get rid of biofilm. Maybe a stronger treatment, maybe a longer contact time, or maybe a different chemistry was needed. And this was checked in real time and online. But going to something more relevant to agri-food, water is used in many food production processes. In this case, for example, water from a well was used to flush the piping of this yogurt production plant when it had to change the flavor of the product. And this water was continuously treated with physical treatments, UV and filters. So water was nearly sterile. Nothing, of course, is 100% sterile, whatever the treatment, but the water was really clean. So chemical sanitation of piping was applied just every 3 weeks because water was really clean. Every day they sampled the water and analyzed it in lab. What did they see? Sometimes 0 colony forming unit in the liquid, so no bacteria, but sometimes very large bacterial counts. So why so large fluctuations? They thought that low bacterial count in water samples was linked to low contamination entering the process from the well. And they thought that high bacterial count in samples was due to high contamination from the well. But this is most unlikely, in particular for well water, and when they replaced the filter with an additional cost, the problem was still there. They did not solve. So they still had large fluctuations in bacterial count. So they adopted online real-time biofilm monitoring, and you can see that just after chemical sanitation of the pipe, biofilm immediately started to grow again. And this is an alert because, as we have discussed earlier, when biofilm is fully removed, it takes time for it to colonize the system again. On the contrary, when it grows immediately after treatment, it indicates that it was not fully removed. So in this specific case, online biofilm monitoring allowed to understand that the contamination was not coming from well, but the clean water that was treated with UV and filter got recontaminated because of existing biofilm in the system. So to solve the issue, they had to increase sanitation frequency. Every 3 weeks was not enough in this case. So what is the return on investment of this kind of approach? It is large and fast because if you have a large industrial plant using chemicals for sanitation, you can drastically cut the amount of biocides you use. Of course, there is a large advantage from the environmental point of view also. But also for food and beverage manufacturing, there is a very good advantage because you prevent contamination and it repays very quick. Also, if there is any heat exchanger in the system, you can drastically increase the efficiency because biofilm is highly insulating from the heat exchange point of view. So return on investment is very, very fast. So this was just to give a brief intro, so we saved also some minutes because we were a bit late on schedule. If there is any question, I will be glad to answer, of course.
Thank you, Giovanni, for your nice presentation. There is a question from Alfieri. Just a moment. I will translate it in English. The algae technologies is can be applied also to apart from clean water to other environments with relevant concentrations of biomass, such as the monitoring of the bacteria fouling in bioreactors, in membrane bioreactors for the treatment of residual wastewater.
Yeah, good question. Of course, it depends on the amount of deposit accumulating on the system. So for very dirty systems, this is not suggested because we detected very first phase of biofilm. But for example, we work in monitoring raw milk. Raw milk has a huge amount of bacteria, of course. There it is possible. Wastewater is more difficult, of course. So it depends on the kind of application, but yes, not just clean water.
Okay. There is no other question from the audience. I have just a last one. So do you think that we are underestimating in the current monitoring approaches the potential of these biofilms?
Yeah, sure. But people are more and more aware, because sometimes now when there is an outbreak in the system and they are not able to locate the root cause, they think maybe it's biofilm. And yes, in most cases it is. We have seen a couple of examples. Just looking at the liquid gives a limited idea, because somewhere hidden in your system, biofilm can lurk, can be hidden. And if you do not look at biofilm, you lose a large part of the problem.
Yes, thank you. So thank you very much, Giovanni, and to all the speakers and to everyone who joined us today. So we have reached the end of today's session. I think that we can have some key takeaway. We can say that real-time monitoring coupled with the artificial intelligence will be key to spread and to push, let's say, the use of reclaimed water in all the sectors, including the agri-food sector. So, and this will need the support of regulation and stakeholders engagement activities, so to increase the trust on this on a safe use of this water. So I guess that we can close the session. I don't know from what are you, if you have any comment.
Thank you very much, Francesca, for monitoring and moderating this webinar, and thank you to all the speakers. And I hope you enjoyed this webinar as much as we did to organize it. And we hope to see you soon for a new one. So thank you a lot to everyone.
Thank you. Have a nice day.
Bye.
Thank you so much.
Thank
Bye.
you. Bye-bye.
Thank you. Bye.
Thank you, everybody. Bye-bye.